Hello everyone, my name is Mahni Fatahi and I'm a PhD student at the University of St Andrews, Scotland. I'm part of the Marie Curie doctoral network TADFSolutions and I work on the design, synthesis and characterization of thermally activated delayed fluorescence emitters for OLED applications. I want to take you through a typical workflow in our lab. First, we design a new molecule and perform theoretical calculations on the new design. Then we create a synthesis plan and perform the synthesis. The crude compound then undergoes purification. Once we obtained the pure compound, we can perform chemical and optoelectronic characterization. For the molecule design, we first take a look at the targeted properties, then we do some literature research, and last but not least, our own creativity and experience comes into play. For the theoretical calculations, it's important to select the correct method beforehand, and afterwards we need to take the time to evaluate the results. When it comes to synthesis, we first look into literature for similar reactions, then we plan ahead the multi-step synthesis, followed by checking or ordering the necessary chemicals. Then we create a lab book entry to calculate the scale of the reaction, and last but not least, we perform the reaction in our lab. Once the crude compound is obtained, it's time for purification. This can be done with column chromatography, such as gel permeation chromatography, manual column chromatography, or flash column chromatography. Another technique is the so-called recrystallization, and last but not least, for the final purification step, we have the vacuum sublimation. Once the pure compound is obtained, it's time for chemical characterization. This can be done with gas chromatography, mass spectrometry, elemental analysis, NMR spectroscopy, X-ray diffraction measurements, and high-resolution mass spectrometry. Once the chemical structure is confirmed, we can tackle optoelectronic characterization. Here we have multiple instruments to our hands, such as a UV-vis absorption spectrometer, a spectral fluorimeter, with which we can measure steady state and gated emission lifetime at various temperatures, and photoluminescence quantum yield under nitrogen and air conditions. Another instrument we can use is the CV-DPV potentiostat, where we can measure the oxidation and reduction potential of our compound. Once a compound went through all these processes, we will get in touch with our collaborators at the TADF Solution Network, and they will take care of this device fabrication and device investigation.